Welcome to lecture 39. We are talking about temperature measuring instruments. In our previous lecture, we have talked about RTD, which is based on changes in resistance with change in temperature. So, we will talk about another instrument which work on the same principle, and this is known as thermistor. So, both RTD and thermistor work on the principle that the resistance of an resistance element will change with change in temperature in a reproducible manner. So, by measuring the change in resistance, it will be possible to relate temperature with the change in resistance, and the change in resistance can be easily measured using a Wheatstone bridge. So, we have talked about thermal expansion methods, complete thermoelectric sensors, thermocouples we have talked about, and resistance temperature device or RTD we talked about in previous class, and now we will talk about thermistors. So, today's topic is thermistor. So, what you see is some images of thermistors. May come in several colors. This is also a thermistor, is written as NTC. So, we will see what NTC stand for. Now, very much similar to RTD, like you have seen in our previous class that RTD is nothing but a resistance element. It may be a wire or it may be a thin film. So, essentially it is a wire or a thin film which work as a resistance element. Exactly similar to this, we also have thermistor, which is nothing but a resistance element. RTD was made of metals, thermistors are made of semiconductor materials. So, their material of construction is different. RTDs was made of metals, and the alpha value, that is the temperature coefficient, was positive because it is positive for metals, but for semiconductor materials the temperature coefficient is negative. So, they are known as negative temperature coefficient resistance element or negative temperature coefficient thermistor. So, that is NTC. Also PTC is also possible, positive temperature coefficient thermistor, but commonly we will have negative temperature coefficient thermistor. So, now what you see here are the images of thermistors. But if you look at a thermistor in lab or industry, what you will see is this. A temperature measuring instrument based on thermistor, if you look at, you will see this. So, this is the protective case and this is there inside this or similar resistance element, and this is the extension leads. So, basically from outside it may not be very easy to find out whether this one is RTD or thermistor, because the protective casing may look identical. Yes, but if it is a 3-wire connection, if it is a 3-wire RTD connection, then I will see 3 wires are coming out. If it is 2-wire connection, only 2 wire will come out. Thermistor generally 2 wires will come out. So, a 2-wire RTD and a 2-wire thermistor, it won't be possible to figure out which one is what just by looking at that. So, you need to read the label, it will be written whether this is a thermistor or whether it is RTD. Whenever you look at an instrument, always try to read the label. Manufacturer supplies several important informations in the label. So, thermistors are thermally sensitive variable resistors. They have either a negative or positive temperature resistance coefficient. They have a high temperature resistance coefficient and the resistance is a nonlinear function of absolute temperature. This makes them very good device for temperature measurement over a narrow range, but more difficult to handle wide range applications. They are available in great variety of sizes and shapes. So, this is how we indicate thermistors with negative temperature resistance coefficient. In short, we call NTC thermistor. And this is how we indicate thermistors with positive temperature resistance coefficient. In brief, we call PTC thermistor. Note that the difference lies here, minus T degree and plus T degree. Plus T degree stands for PTC thermistor or positive temperature resistance coefficient thermistor, and minus T degree stand for negative temperature resistance coefficient thermistor or NTC thermistor. So, this is schematically shown how resistance changes with increase in temperature for NTC thermistor. For RTD, you have seen how the resistance increases with increase in temperature for platinum, nickel, tungsten, etc. In case of NTC thermistor, resistance decreases with increase in temperature, and this is highly nonlinear relationship. And you see the resistance rapidly falls. The resistance rapidly falls for a small increase in temperature. So, the instrument becomes very sensitive, but it is highly nonlinear. So, calibration will be very nonlinear. However, PTC thermistor or positive temperature coefficient thermistor is also available. Here you will see that initially the resistance decreases with increase in temperature similar to NTC thermistors, but then there is a temperature which we call switch temperature. There, after that switching temperature, with increase in temperature, the resistance increases similar to platinum, nickel, etc. So, these are switching type thermistors. This is a relationship which tells us how the resistance will change with change in temperature for NTC thermistor. You can see the relationship is highly nonlinear. R2 equal to R1 into e to the power beta into 1 by T2 minus 1 by T1. T1, T2 are temperatures expressed in absolute scale. Beta is thermistor constant and R1, R2 are resistances at temperature T1 and temperature T2 respectively. The high sensitivity of an NTC thermistor makes it an ideal candidate for temperature sensing applications. These low cost NTC sensors are normally used for a temperature range of minus 40 degrees Celsius to 300 degrees Celsius. Please note that the temperature range is not very great, but in this temperature range the thermistors are extremely sensitive instruments, and also it is low cost, inexpensive, because these are made of inexpensive semiconductor materials. Another important aspect is that they come in various sizes and shapes. So, the selection criteria for NTC thermistors are temperature range, resistance range, measuring accuracy, environment or the surrounding medium, response time and dimensional requirements. So, these are the factors which will govern the selection of NTC thermistor. What is the range over which the temperature will vary, what is the resistance range, what accuracy is required, what kind of environment in which you have to perform the temperature measurement, what is the response time and what is the dimensional requirement. So, the change in resistance of NTC can be measured as usual by a Wheatstone bridge principle. So, here the NTC thermistor is used as one leg of the Wheatstone bridge. Now, the NTC thermistors are made from semiconductor materials. So, NTC thermistors are basically semiconductors and they are made from mixtures of oxides of nickel, manganese, copper, cobalt, tin, uranium, zinc, iron, magnesium, titanium and other metals. So, they are made from mixtures of several oxides such as nickel, oxides of nickel, manganese, copper, cobalt, tin, uranium, zinc, iron, magnesium, titanium and other metals. The oxides are milled and mixed in proper proportion with binders. Then it is pressed into desired shapes and sintered at around 1000 degrees Celsius to form thermistors in the form of rod, disc, flakes or beads. So, these are the common shapes. So, as you see, the materials it is made from are oxides of nickel, manganese, etc. So, they are all made from inexpensive materials. So, these oxides are mixed in various proportions, they are milled and mixed in various proportions and they are also mixed with binders, and then it is pressed to give different shapes. The shapes commonly are rods, discs, flakes or beads, etc. The type and proportion of oxides used, the sintered atmosphere and the sintering temperature determines the resistance and temperature coefficient of the NTC thermistors. So, this is important. The type and proportion of oxides used, the sintered atmosphere and the sintering temperature determines the resistance and temperature coefficient of the NTC thermistors. So, these are two important variable for the thermistor. One is the resistance of the element and the temperature coefficient, and you can have a control on these two variables by changing the proportions of oxides, sintering atmosphere and the sintering temperature. So, this shows various sizes and shapes thermistors. So, rod type, disc type and bead type. We have seen this is the symbol for thermistor, and as it is minus T degree. So, this is a NTC. PTC thermistors are of two types. Made from silicon, they are called Thermistors, have uniform positive temperature coefficient. Thermistors have lower sensitivity than NTCs, but their resistance temperature characteristic is more linear. So, thermistors made from silicon known as Thermistors have uniform positive temperature coefficient. The other type made from barium, lead and strontium titanates with the addition of yttrium, manganese, tantalum and silica. These are switching type PTC thermistors. Switching PTCs have extremely high sensitivity in a narrow range of temperature centered at the Curie temperature of the material. The PTC thermistors finds applications in self-regulated heaters, overload protections and also in introducing delays. Here are some advantages and disadvantages of thermistors. The advantages are thermistors have large temperature coefficient which make the thermistor a sensitive device. Accuracy of measurement can go up to 10 degree Celsius, plus minus 10 degree Celsius. They can easily withstand electrical and mechanical stresses, low cost, good operating range minus 100 to 300 degree Celsius, of course not as large as thermocouples or even RTD has much higher range. Another advantage of thermistors is they can have small size. Small size further adds to improve sensitivity. Disadvantages mainly the temperature resistance relationship is nonlinear. So, the calibration is highly nonlinear. This shows a comparison among the output voltages from thermistor, RTD and thermocouple. Among these you see that RTD is most linear. Finally, we put some comparison of various sensors and summarize their advantages and disadvantages. Thermocouples has linear output, it requires reference and has low sensitivity. RTD output is linear, large temperature span, large resistance range. Disadvantage low sensitivity, high cost and vibration sensitive. Thermistors advantages are high sensitivity, high accuracy, fast response, low cost, vibration resistant. Disadvantage narrow temperature span compared to others and output is nonlinear. Next, I want to show you a bimetallic thermometer, a thermocouple, a RTD and a thermistor. So, let me first show you a bimetallic thermometer. So, this is a bimetallic thermometer. So, what you see is this is the dial. So, this is the dial. you can see the pointer and scale. So, the scale will be calibrated directly in terms of temperature units. And you see this is the protective case. Inside there is a bimetallic strip. In fact, most likely there will be a helical coil made of a bimetallic strip. So, this is completely encapsulated. So, this will be inserted to the medium whose temperature I am measuring. So, this end of the bimetallic strip is rigid inside the protective case, and the other end of the bimetallic strip is connected to this pointer through some gear and linkage mechanism inside. So, when this part goes to the medium whose temperature I am measuring, the bimetallic strip receives the temperature, shows the deflection, which will cause the movement of this pointer against the scale, and you can have a direct reading of the temperature. You can see this scale is 0 to 100 degrees Celsius. So, this bimetallic strip, this bimetallic thermometer will measure temperature from 0 degrees Celsius to 100 degrees Celsius. So, from ice water to boiling water. So, next let us come to electrical method of temperature measurement, and what you see now is a thermocouple. So, you see two identical protective cases. So, we have already seen that the thermocouple is made of two dissimilar metals and they are joined end to end to form two joints or two junctions. One we call cold junction or reference junction, and the other one we call hot junction or measuring junction. So, one of them is hot junction or measuring junction, another one is cold junction or reference junction. So, I can, let us say if this is the cold junction or reference junction, I can put this into ice water or known 0 degrees Celsius and can put this to the medium whose temperature I am measuring, and this will be, these are the extension leads which will be connected to the a millivoltmeter. So, millivolt, that is output from the thermocouple, that reading has to be compared from the thermocouple EMF table. You now look at the thermocouple EMF table and see the output of the millivoltmeter corresponds to what temperature. So, you are already putting this into 0 degrees Celsius. So, no correction is needed. If it is not put to 0 degrees Celsius, but some other temperature, then a correction is needed. So, what correction will be added? The EMF that will be produced when the two junctions are kept at the reference temperature you are talking about now and the 0 degrees Celsius. So, this is a thermocouple. So, thermocouple, remember, will have always two such elements. So, inside these two protective cases there are two joints. One is hot junction or measurement junction, another is cold junction or reference junction. So, next I will show you this. This is another temperature measuring instrument. Again, electrical methods, and this was thermocouple. See, you cannot find out any difference at all. Now, you see here I have 3 wires coming out. So, 2 white and 1 red. So, 3 lead wires are coming out from this device. So, this is a resistance temperature device. This is a 3-wire RTD. This is a 3-wire RTD. So, inside you have a resistance element. Let us say a platinum wire wound around some say a glass support or ceramic support, and then these 3 wires tells me that this is a 3-wire RTD. Finally, I will show you exactly another one in look, but this is a thermistor. This is a thermistor. So, first it was thermocouple. This thermocouple is actually K-type thermocouple. So, this thermocouple is K-type thermocouple, and you know the K-type thermocouple is a chromel alumel thermocouple. So, you have a chromel metal, you have an alumel metal, and you have made 2 junctions. So, there is one chromel alumel junction here, there is another chromel alumel junction here. So, in these 2 protective cases, there are 2 junctions which you have formed by joining a chromel and an alumel. And this 3-wire RTD is basically a PT100 RTD. This is a PT100 RTD. So, if I put this into ice water mixture or 0°C water or 0°C source, the resistance that you will measure here is 100 ohm. So, this is a PT100 RTD. So, with this we stop our discussion on thermistors. So, as of now we have talked about temperature measuring instrument based on principle of thermal expansion of material. Then we have talked about thermocouples, which is based on thermoelectric principles. Then we have talked about thermistors and RTD, which are based on the variation in resistance with change in temperature. So, in the next class we will conclude our discussion on temperature by after discussing temperature measuring instrument based on radiation principles.